Full Throttle RC presented by Warehouse Hobbies. I'm your host, Tony Castronovo. This is part C of our three-part series on engines for model boating. This is the part that we're going to get into and actually talk about the engine work. We've already talked about theory in episode 1, or episode 2, I guess, part A, and the second was degree wheel, how to use a degree wheel to establish your timings, and the third is going to be the actual hands-on engine work. So stay tuned, and we're going to get into modifying your own engine. Okay, the first thing we're going to do when we modify the engine is the compression. This is the single most important part on a combustion engine. This is the distance between the outer diameter of the top of the piston to the outer diameter of the head. And the least amount of space shown over here, we'll use our home light test engine again, right here. Chris will zoom in. The least amount of space between here is going to establish the most amount of compression. And compression is simple. We're going to squish the air and the gasoline charge, and we're going to crush it till the gasoline turns from a liquid to a vapor. Compression is the single most important part of making horsepower. There is no doubt about it. This is the most important part. Now, to establish this, we obviously cannot let the piston make contact with the head. So we try to establish a good, what we call deck height. And what I've established on the Zenoas is about 10 thousandths. We've talked about that before. That is a safe deck height. We've done a lot of testing with this, and we found the best performance at about 10 thousandths. This allows for any type of a slop in the top bearing, between the rod bearing, and it works really well, and it's great. So what we're going to do before we get started is we've got to talk about the tools required to do this, because there are certain tools required. Okay, first, you want to have a set of calipers. Digital preferably, they're easier to read. Second, you're going to need a depth indicator. These are very simple and easy to find. They're available at most any machine tool online store or any machine tool retail store like Harbor Freight, for instance. Very inexpensive. You can get them under $15, $20 now. Okay, it's got to be modified slightly to work for our application. So here's how we're going to go through this real quick, and then we'll get into it in detail. The home light that we're going to use, because I have the cutaway version, easier to see. Again, it's very similar to the Zenoa engine, but I want to use this because it's easy to see. It has a different spark plug thread. It's a larger diameter than the Zenoa. So you have to make a piece. Just zoom in here. You have to make a piece that can adapt the shaft of the depth tool, okay, to the spark plug hole. And what I've done in this case is we took an old spark plug and we simply figured the diameter, the 3/8 diameter, for instance here, and we drilled it. We took the element out, the electrode and all that, and we drilled it out. So we made ourselves a sleeve that this could freely slide on, and then a set screw to tighten it down. This is how we're going to establish our deck height, this particular tool. So it's easy to make. Again, we used a depth indicator tool, an old spark plug, drilled out so it fit, and we drilled a hole in the side and put a set screw in it so we can adjust it. And we'll go into that in detail in a few minutes here. Okay, we removed the cylinder from our home light show engine to show you what the next procedure is. And what we're going to do, and again, remember, the Zenoa, the home light, they're the same basic principles. We're just going to use this engine as a test vehicle because we can see the internal function of how things are taking place. Okay? We're going to take a piston, and we're going to push it into the cylinder, not attached to the engine, all the way to the top, all the way up, as far as it goes, okay? And do this a couple times. I'm going to show you with the Zenoa what I'm talking about. I'm going to take a Zenoa piston and a cylinder. I'm going to do the same thing. Obviously, this tool would be in this unit right now in the Zenoa cylinder. We're going to take the piston with our finger. We're going to push it all the way up to the top. We're going to make sure it's seated all the way up there real good. That's it, okay? So let's go back and show you what's taking place here. We're going to do the same thing here, and we got it to the top. And once we establish the top, check it. Do this 2 or 3 times. Don't take the first numbers, for granted. We're going to take the indicator, and we're going to zero it out once the piston is at the extreme top. Okay? Zero it out. Tighten your thumb screw. The thumb screw tightens the wheel so that the dial indicator part can't move. Okay? It's very important at this point that this does not get disturbed. You don't turn this. This should be seated very well before we got to this point. So make sure you turn your dial indicator in all the way so it can't move. If it was to move left or right, it's going to change this. It's going to affect the height of the unit, which is going to therefore change the number here. But here's what we have. We've established top where the squish band is making contact with the cylinder head, and it's at 0. Okay, there's only one real factor more that has to be taken into consideration, and possibly two if you're doing a home light. With the Zenoa, the factor, and the home light again, the factor is the gasket. You have to compensate for the thickness of the gasket. If we're going to achieve a 10,000ths clearance, we have to compensate for the thickness of this gasket because it's going to go between the cylinder and the block. So we're going to take our gasket. These might look a little different from you. We manufacture our own gaskets in this company. So, but the paper gasket that's supplied by Homelight or Zenoa, treated with the right treatment, which we'll get into in a little while, works fantastic. Okay, we take our gasket, we mic it, and we're 18,000ths of an inch. And same with this, same material, different engine, 18,000ths of an inch. Let's take that 18,000ths and just write it down so you know. Now, normally when we do this, we know the squish factor on the gasket's about 1,000, so we take that in consideration. But since you're new at this, I kind of like you to do this next procedure with the gasket. So this way you don't forget to compensate for the gasket. Because if you were to forget, you would take the material off that the readings are going to give you, and you would end up smacking the piston in the top of the cylinder because you forgot to allow for the additional 18,000ths of the gasket. So let's put the engine back together with the gasket on it. And this is a little tricky. Let's see if we can get this together quickly, which we did. And I'm going to bolt it together too, because I want these numbers to sort of be correct. Now this is loosely done. Okay. Now you guys are going to get the idea of what's going on here and why we went and zeroed out the indicator and compensate for the gasket. Okay. We know now when this piston is not connected to the crankshaft and shoved up, we read a 0 on the indicator. But that's not the case when it's assembled because you have to compensate for the thickness of the flange on the base, the thickness of the gasket, the thickness of the flange on the block itself. Okay? So we're going to bring this engine to top dead center. Remember top dead center from episode, I guess, theory number 1, episode A on engines, showed you the top dead center was at 12 o'clock. And now we're going to read the gasket. Read the dial indicator. And this engine has already been modified. This is many years old, and we use this for show, but it's been modified. So I know the original numbers, and these engines tend to have showed a differential of head clearance between 35 and 45 thousandths. So let's say that it was 35 thousandths at this point. Okay, you brought up top dead center, it's 35 thousandths. So we're going to mark down 0.035 for reference, and we're going to say that's the actual head clearance. So you can put down head clearance before modification. Okay? Now it's pretty simple from here. We already have the gasket in place, so we've compensated for that. So now, remember what we talked about? We talked about establishing a 10,000ths head clearance, squish band. So if this is telling us that we're 35 thousandths, then if you deduct 10 thousandths from the 35, that's going to leave 0.025, 25 thousandths of an inch. Real simple now. That means that if you remove 25 thousandths of an inch from either the cylinder bottom or the base crank case, the top of the case, or half from each, doesn't matter how you achieve that, you will then establish a 10 thousandths head clearance on this engine when it's reassembled. Okay, again, I disassembled the engine. I want to show you what we're talking about when I said take some material off either the top of the crankcase or the bottom of the cylinder. In the case of Homelight many years ago, it was more of a high-speed production engine made for the string trimmer industry only. So these engines were built off of several castings. The castings, they weren't critical. You guys need to know this. There's a big difference between Zenoa and Homelight when it comes to quality. The Homelight engine was designed to produce 1 horsepower. That was it. I mean, that's what Homelight needed for that string trimmer. It was not a purpose-built engine. So things weren't, the quality of the manufacturing really wasn't up to par what we required. So we used to have to take, and I'm going to walk off track a little with Zenoa, but I want to explain this because there's still guys out there building home light engines. We used to take and resurface the actual top of the crankcase here. And you can see that it's been machined. So when we talked about 25 thousandths, I would take a fly cutter, we had fixtures to do all this, and we would fly cut up just enough to get a good smooth finish. And that usually only took about 10 thousandths. 10, 12 thousandths, I don't remember exactly. But once we achieved that, remember we have 25 thousandths of the roof, we would take that 12 thousandths, we'd have to deduct that from the 25 thousandths. Okay? Then the difference, we would then take off of the cylinder base, right here. And we'd have two good matched surfaces. No longer do we have a rough sand cast surface here and a cast surface here. Now we have two machined surfaces. But when we put them together with the gasket, we achieved that 25 thousandths that we're talked about and the 10 thousandths head clearance. Okay? So let's talk about the Zenoa now, because you don't have to go through this kind of craziness with the Zenoa. The Zenoa engine is a very high quality engine. The machine work is fantastic. I've sold thousands of them, literally thousands of them. We check consistently to see what their tolerances are, and Zenoa holds real close to 2,000s, plus minus 2,000s. So the case being fly cut already, part of their production, that's not necessary to do. The cylinders are cast, they're die cast, and this is where we're going to remove our material right here. So remember, we have to remove 25 thousandths. We make a mandrel. We have a mandrel on the lathe. We have a specific lathe just for this, that the cylinder slides into a mandrel. The mandrel is attached to the live end. It bolts through, and it spins the cylinder. Okay? Then we take a cutting tool, very simple. We go in and make contact with the base of the cylinder, set the indicator on the machine at 0, and now all we have to basically do is go in and cut until that tells us 0.025. But you don't want to take it in one pass. People make this mistake all the time. The less amount of passes you make, pass meaning how far deep you're going to cut and how many you have to do, the better the finished surface you're going to get. So I found that it's good to take 5 thousandths passes at a time. Now we have to establish 25, so that's simple. That would say five passes. Not really. Let's do this in 4 passes, and I'm explaining why. Let's take 5, 10, 15, 20 off, which we're going to go in, we're going to touch at this point here, set at 0, bring the tool out, bring it back in to clean anything we might have missed, go back down 5 thousandths. Let's do this 4 times. Now we have we've achieved 20 thousandths. Okay, the last 5 thousandths, let's do this in 2 passes, or maybe even, and the reason being is because the less you dig into this material, or any aluminum for that, or steel, the better the surface finish is going to be. So let's say that we went in at 3 thousandths, and we pulled back and went back in. That would leave us 2 thousandths. A 2 thousandths pass is good, or 1 or 2 thousandths. You can do 2 more if you want to do it one at a time. But bottom line is you want to stop at the 25. And you want a nice smooth finish. It does not have to be baby skin smooth. If you put your fingernail and felt, like a thread feel, that's fine too, because we treat these gaskets, and the material we treat actually works better if it has a little bit of a rough finish to it. Anyway, that is called decking the cylinder. You've heard it a million times. And what that means is we've removed material on the bottom of the cylinder, the base of the cylinder, which lowers the cylinder to the block, which raises the height of the piston and establishes the head clearance. And we're shooting for 10 thousandths of an inch on head clearance. Okay, before I go any further, I want to give you guys a little bit of my background on engine work. Some people think that I've just started doing this a couple months ago, and that's not the case. I want you to feel confident in what I'm telling you and showing you. And I'm going to go back and tell you how I started and how I learned, and this is how I'm teaching you. I raced motocross, started motocross real young, 10, 12 years old, 2-stroke engines, back in the day where there was no such thing as modified engines. I go back to some of you guys will relate to this. I think one of the first bikes I raced was a Hidaka, and they were pretty basic. And when I started to excel, there was a lot of engine work that had to be done to get you into the next class competitively. And from there, I went into racing midget cars. And there was a class that developed, and I don't want to make this about me. I just want to give you I want you to feel confident, so I'm going to give you my background here. There was a class that came up in Fort Lauderdale back in probably 1976, 77, if I remember. I was probably 15, 16 years old. And we raced these midget cars. They were not full scale. They weren't quarter midgets. They were somewhere in the middle. And they were allowed to be powered with two-stroke engines. And back then, Yamaha made a RD engine, RZ engine was out, the Kawasaki had a 550 out, if you guys remember that, a 350 and a 550, and I think Suzuki even had one. And the parameters of this particular class was from 440 cc's, I think we can go to 550, and it was a stock class. And I ran this, and I did really well with it for about a year. And then I wanted to go into the next level, which was called Outlaw, and that was where the big guys hung out. And I took my car, and I never forget running the first night of Outlaw, and boy, did I get my ass whipped. It was sickening. But I was a young guy, and the older guys that were racing against me kind of took to me, and they started showing me things. So what I'm showing you here today is so basic, it goes back, this concept goes back probably now 75, 80 years. As a matter of fact, one of the old gentlemen that taught me this, they're all deceased unfortunately right now, would always make a comparison between our engines to an old Westinghouse washing machine engine that Westinghouse used to make, I think, at the turn of the century in the early 1900s. And you can quote me on this. And this was an outside washer. Well, I think the first washing machine that was motorized, and you had to kickstart it. And it was a piston port engine, very simple design. And it is, with the exception of that, we've learned more about metallurgy today. And we've learned about better head configurations and piston configurations, such as the hemispherical head, and and lubricants. The concept is the same as it was during those days. And you can quote me on that and look it up in Google and look at those old Westinghouse engines. Anyway, they taught me about how to get the most out of a piston port engine, which I was using. And some of the guys were into reeds and all kinds of crazy stuff in the early days, in the 70s with this. And we basically stayed with the piston port. So what I'm teaching you here today is what was taught to me back then. And the fundamentals are the same. The practices are the same. You're trying to make the engine as efficient as possible. Remember, these engines aren't very efficient. Piston port engines are not efficient. So we're gaining the efficiency on them, trying to establish more horsepower and more top end. And this is where the basis of my knowledge comes from. So contrary to some people that believe that I just started doing this, a few months ago, it's not the case. In reality, I made a decision. It was a tough decision back in the late 80s, and Enforcer started to get pretty popular. I had commitments of shipping boats all over the world. It was not uncommon to take orders, annual orders for one particular distributor, over 150 boats. I had to make a decision back then, and I had a heck of a guy working with me, Robin Loy, that we did all this engine work. I had to make the decision to do away with this competition program because I couldn't do it all. I couldn't get into this productive area of the gasoline, which is the masses, and that's the direction I wanted to go, to be able to sit here today in a television studio that we own. I mean, this was all necessary to make the funds capable of what you guys are experiencing today, and we're proud of that. Engine modification. Let's go back to when we started this. I remember starting Enforcer going to the Builder Square, I don't think they're in business anymore, and buying Echo engines back in 1981. And we would put them into boats and sell them to standard regular customers in my store when I first had a store. And they weren't fast. I was a nitro guy. I was just doing 40, 50 miles an hour. These boats were running 25, 28 miles an hour. But that particular element that was purchasing them, they loved them. They liked the ease of it. It wasn't too far after that some of my customers started to become competitors. One particular gentleman, which we had a love-hate relationship for years, but I respected him more than anything, because if it wasn't for him, he probably wouldn't have pushed me to go forward as I did today. And that unfortunately, he passed away a couple years ago, and his name was John Mellis from International RC. And John was one of my customers who bought one of the first original Forcers. And John used to work on Fiats, and he started pushing the performance end of it. And between him and myself, we would compete, and we started doing engine work. So we date these engines back. I would say Warehouse Hobby started model gasoline boating modifications in the industry, and that dates back to 1980, probably 1982, 83. Prior to that, the conception of this whole industry was basically started by Tom Persinka, the owner of Octernal. Whereas Tom used an engine back in the early 60s, 62, a year after I was born. So, you know, he was the actual father of this gasoline model boating, where Tom used Olson and Rice engines. They were called O&R. And they were the predecessors of today's string trimmer engines. These engines were used on everything. I mean, they were in the 60s. You can go back to old Popular Mechanic articles, and they started making sickle cell cutters for hedges. And then they were putting them on bicycles. And then they were making backpack propeller things with roller skates. I mean, I saw the weirdest stuff being done with these engines. And Tom used one of these engines, and they were little 1-horsepower gasoline ignition engines in a boat called the White Heat. And and that was the original conception of gas model boating. But it was very expensive. Back then, a boat and a radio back then. I remember my grandfather buying radio equipment in the late 60s for $700, $800 for a 2-channel transmitter. Well, you combine that with $700, $800 on a boat, and do that in 1968 money, $1,800, $2,000, and that's what happened to the industry, and that's what I believe why it perished. I knew of it in the early 70s. I remember, you know, I remember my grandfather was into this. I remember it. When I took the concept in the late 70s and early 80s, it was the right time. And that's how it's evolved into what it's evolved today. So I didn't want to get too far off track. I just wanted to let you guys know that what I'm telling you is not something I've concocted. I've learned a lot off of it, but I've relied on older gentlemen 4 decades ago to teach me this. And I'm not afraid of learning. I learn on a daily basis, and I do. I purchase other competitors' engines and see if there's anything that I'm missing or anything more I get done. We just recently purchased a very expensive water brake computer interface dyno. Something we really didn't need. I mean, our engine program is pretty great, but now I want to get down to the nitty-gritty. I want to find out what we're really making for horsepower. I want to read in tenths so we can really learn this. Also, I can educate you on what you're reading, what you're hearing. So in the future, you're going to start seeing, we're doing a blog on the site where I will start writing my findings, and you can see that with some of the dyno results on the internet right now that I've provided. Anyway, I got a little off track. We're going to get back into the next procedure of modifying an engine when we get back. New product from Enforcer. Let me show you our new carburetor air cleaner diffuser. This little device is designed to connect to the Enforcer velocity stack or the stack that comes out of the G260 standard carburetor in a Zenoa. And it is made of a fine mesh screen that will allow only air into the engine. And any kind of debris from the hull that might get in your hull, keep it out of the engine, which can cause severe damage. They're very easy to assemble. They can be purchased as the diffuser only for $9.95, or they can be purchased in a kit, including the Enforcer velocity stack, I believe for $19.95. Very simple. Whether you use the Enforcer velocity stack or the Zenoa horn that comes on the carburetor, you put the velocity stack in, and the material around this rim simply gets peened over with a screwdriver, and it's securely in place. We also include a rubber cover, so when your boat's in storage, you keep anything out of the carburetor. Also, it can be used to choke an engine if you're using an engine without a choke. We do recommend that you use this particular product with engines with a choke. It does make it easier. On a dyno, it has zero effect on performance of an engine. So it has been calculated and designed to let the proper amount of air in. It also diffuses the water, which is a great thing. So if you were to go upside down in a boat, the big lump sum of water doesn't enter the velocity stack. It enters the screen and diffuses it, and it limits the fact that you can bend a rod. Now, there's no guarantees, but it does work real well in its intent to do that. This is called the Enforcer Carburetor Air Cleaner Diffuser, and it's available now through Warehouse Hobbies. You can call and order one at 1-800-444-1995. Okay, let's get to the next procedure. And what I'm showing you today is I'm going to show you what basically we do when we produce what we call our M5 engine, which is actually motor 5 for us. We produce up to a 6. We produce an M6, which is our competitive race engine. But I want to show you the M5 because it's a user-friendly engine. You can do this work yourself. You can do it with hand tools, and it makes a big difference in performance. And it doesn't take too much out of the bottom end or make the engine too finicky, and it can be used successfully with a clutch. So I'm not going to go so far into detail with every little trick, because there's a lot of little things that can be done to pick up minute improvements. And if you're in competition, that's very important. But for sport boating, what we base our company on, and for practicality to what you can basically do in your shop, we're going to deal with the M5 engine. Okay, first thing we want to talk about is the piston. We go past the fact that we have the engine already decked. We have that finished. We know we have a 10,000 squish band. That's done. So the next thing we're going to do is we're going to take the piston. And we got to do a couple little things here. And what I'm going to tell you is basically what I get off of the engineers. I like to communicate with the engineers of the engines to talk with them on their designs and the reasons they do things anyway. This particular engine, the Zenoa, is an excellent engine. The metallurgy is phenomenal. We all know this. It's basically propelled our industry. Unbelievable. It's been around, 4 years now, and it's just unbelievable. It's the motor of choice. Okay, they designed this engine, the 260. Let's use that one. They designed that engine to run at roughly 3 horsepower at 12,000 RPMs. And talking to the engineer, he was telling me that they get about 200 hours out of. That's how they test them at 12,000 RPMs. The heat signature, meaning the heat that the engine produced, is calculated in, and that would mean that the piston clearance, the distance between the piston and the cylinder, is calculated in for the particular engine's design and how it's going to run and operate. Once we start doing modifications, we're altering that design. And there's a chance when you're altering in a design, this goes for any engine, there's a chance that you're going to upset the balance of something. Okay? Generally, you modify until the weakest part can't take it anymore and the engine, what we call, blows up. Something fails and rod breaks, bearings let go, and it can do catastrophic damage. But in the case of the Zenoa, the clearance between the cylinder is fantastic, and it's exactly right when you're running them in this format out of the box, the 3 horsepower format. When you start doing work to these engines, especially the exhaust timing, which we'll get into in a few minutes, you start changing the heat signature. And when you change the heat on an engine, what happens when you heat something? You have expansion. Molecular expansion takes place. Your piston is made out of aluminum, it expands. Your cylinder is made out of aluminum with a chrome lining, it expands. Obviously, the two are dissimilar. One expands more, which would be the piston because it's aluminum. And the engine is designed to absorb that heat and dissipate that heat and operate. With the Zenoa engine, you've probably seen this before. You've probably seen articles where guys say, well, we do oil grooves and stuff like that. This is not new. This is stuff we used to do back in the days with the McCulloch go-kart engines. We ran into heat signature problems because back then they didn't really know that you could run an engine as loose or sloppy with a lot of clearance, and it would be better. Most engine companies back then had really tight clearance. I mean, these engines, I think Zenoa told me, don't quote me, but I want to say they said they're 6 to 7,000 clearance, which again is fine in stock. Okay. You hear these articles that say, well, we do oil grooves in our pistons. That's really not the case. It's really not an oil groove, and I want to kind of set this straight. There's a few people I've talked to that actually know what it is, and I'm going to pretty much teach you this right now. When you look at the top of a modified standard Zenoa engine, take a good look at it. Chris, zoom in here. Okay. It's a machine piston, equal on the top as equal on the bottom, and they machine it with grooves. Run your fingernail across it, and you can feel grooves. And the concept of this is to keep lubrication around the cylinder and the piston, and also relieve the amount of friction on the cylinder walls. Because, you technically don't want direct contact with the piston and the cylinder. You don't want that. You want an oil barrier between the two. You have a ring up here, and the ring is what's creating the compression. That's where your power is being made right there, your compression. You're not making compression with the piston. So actually, you want a film of oil around it, no contact, period. If you get contact with the cylinder, it will literally scrub the aluminum off the piston and fuse it to the cylinder, and that's what we call a stick. Okay. Oil grooves. Let me go through this. Take a good look at a modified piston we've done. Zoom in right here, Chris. Okay? We literally go into the piston at the top of the squish band, and we go in about 2.5 thousandths, and we draw down past the ring to about 100 thousandths in depth. And we remove that material from the top of the piston. Now, there's guys that say this is for oil. That's not the case. What happens with the Zenoa engine is when you, and I can't say Zenoa only. I've had this, like I said, this used to happen in the McCullochs. When you get this type of heat exceeding what it's designed to do, the piston gets extremely hot. And the exhaust side, the side with the arrow, that's what the arrow indicates on the top of a piston, you guys, the exhaust side. The exhaust side is obviously the hottest point of the engine. The end piston starts to swell. The cylinder starts to swell. Everything is designed to do this. However, when it exceeds what it was designed to do, the piston will swell and literally make contact with the cylinder. And this is a problem that we found on the modified Zenoas, whether we do the M5s or the M6s. And most everybody in the industry has picked up on this and followed suit. Some really don't know what they're doing, why they're doing it, but they're doing it, and that's what keeps these engines staying together. If you didn't do this, and you did these modifications I'm about to show you, everything I'm about to show you, chances are, I don't care what kind of oil mixture you use, you will have a contact spot roughly, maybe 3/8 of an inch off center of your exhaust window, at this point where the hottest point is, and it will stick to the cylinder, and it will ruin your engine. So, by removing 2.5 thousandths in, down past the ring, I like to go 100 thousandths. Some guys, I've seen them at 60 and 70. We go 100, and it's a very safe number. You are removing the material on that particular part of the piston. This way, when the piston swells at this point, it cannot make contact. It also is completely clearance of the cylinder, allowing the ring to do the work. Less friction, more speed, more piston speed. And that is the purpose for this. So, a mandrel has to be manufactured or made to hold the piston in the lathe. You need to use dial indicators on this. This really needs to be done right. And you want to make sure that piston's spinning true. You can use a dead end. There's a hole in the center here to assure that. That's what they make it. That's what it's there for when Zenoa manufactures it. And then you want to go in and cut back 2.5 thousandths down 100 thousandths past the ring. And that works fantastic. Okay, we've gone through how to deck a cylinder, established the 10 thousandths head clearance to piston. We've talked about modifying the top of the piston. And that's about what we're going to talk about in this episode. And we'll finish, I think we could finish the whole engine building episode up in number 5, which we'll bring out real soon. And they'll give you a little bit of time to watch this a couple times to understand it. You need to make some mandrels. You can get started working on a mandrel to hold your cylinder in the lathe. So that's a real simple thing to do. Take a piece of steel, works really good, round steel, and turn it down till it fits real nice in the cylinder. You could tap the other end of it. We like to use hard steel. Tap the other end of it for a bolt. You can run the bolt in on the mandrel, and then the mandrel on the lathe, and make sure it spins true, and you've got a nice mandrel to work the bottom of your cylinders. That'll give you a little bit of time to do that. Piston, same thing. You can make a mandrel for the piston. We like to utilize the piston pinhole, and we make a device that slides in, put the pin in, and it works great. I'm sure there's other things you can use. Collets. If you're a machinist, you can design a collet where you can slide the piston in and grab it. You know, as long as you get a good area of it, grab it securely like this and spin this. So this will give you guys some time to make these two fixtures to produce these two parts. And when we come back, we're going to get into the end of how to modify an M5 Zenoa engine. I want to thank you for joining me. My name is Tony Castronovo, host of Full Throttle RC, presented by Warehouse Hobbies. We'll see you soon.